All right, here is question 2a. Use the method of Lagrange multipliers to find the maximum volume of a rectangular box with three faces on the positive coordinate planes. Now, all this information is just given to us so that we know that x, y, and z are non-negative, um, or maybe even strictly positive, because if any one of them is zero, then the volume is, of course, going to be zero, since the volume is just x times y times z. All right, and vertical plane ax plus by plus z equals d, that's essentially the constraint, right? So the volume is x times y times z. It is the objective function that we are supposed to maximize, and the plane or whatever is the constraint. Now, I am assuming that we are not supposed to prove that the maximum exists, because this would be quite tricky. All right, so although in the tutorial, whenever we're not supposed to prove that the maximum exists, then it's kind of explicitly mentioned that we are not supposed to do it. But I don't think that it's really reasonable to rigorously prove that the existence of a maximum, right? So, okay, so let me do it. Um, so basically, we have the objective function is just x times y times z. I'm sorry. What's going on? X, Y, Z to the maximum. The constraint is ax plus by plus z equals d. That's the constraint. Now, x, y, z are positive. Well, and all the constants a, b, and d are also positive. Okay, so how do we do this? This is a Lagrange multiplier, so we've got to find to write a Lagrangian function. So it is the objective function x, y, z minus lambda times the constraint. So ax plus by plus z minus d. Right, so then we find critical points of the Lagrange function. So the partial derivative of L with respect to x is yz minus lambda a, and it is supposed to be 0 because we are finding critical points. So we are finding partial derivatives and equating them to 0. So Ly is xz minus lambda b, should be 0. Partial derivative with respect to z is going to be xy minus lambda is 0, and the partial derivative with respect to to lambda is essentially the constraint. So lambda is really minus ax plus by plus z minus d, should be 0. All right, so now the first equation is really just lambda a is yz. The second equation is lambda b is xz. The third equation is lambda. Okay, we know the value of lambda is just xy, which is very, very convenient. And the fourth equation is just a constraint, so it's ax plus by plus z equals d. So how do we solve it? So usually the best strategy, if you don't know better, if any other strategy is not obvious, then yeah, you should find lambda and kind of exclude lambda. So in this case, we actually already know lambda, so we can just substitute it into the two other equations, into the two other equations, and see what's going to happen, right? So now I'm going to replace lambda with xy in the first two equations. So xy times a equals yz. So xy times b equals xz. And very conveniently, y cancels out here and x cancels out here. So xa equals z and yb is also z, right? So xa is this thing, so this is z. By is again is z. So substituting z for xa and z for yb into the constraint, we just get 3z equals d. So z is just d over 3. And now let's find x and y. So x is, from this equation, x is z over a, so which is d over 3a, and y equals, well, by the same logic, is basically d over 3b. Okay, so this is the values of x, y, and z that maximize the volume. So the volume itself is going to be the product of x, y, and z. It's x, y, z, which is d divided by 3a times d divided by 3b times d divided by 3, so which is d cubed over 27ab. So that's the answer.